Welcome to the Explainer. Listen, if you're looking to make the leap into hardware and semiconductor engineering, you've probably already realized that the learning curve can feel, well, a bit like hitting a brick wall. But today, we're going to demystify this totally overwhelming landscape of digital design. We're giving you a highly structured, step-by-step blueprint to transition into a digital design engineer role. Basically, we're turning a massive mountain of concepts into a clear, totally navigable path.
So, here is the blueprint we'll be tackling today. We've got 1. Laying the logic foundation. 2. Mastering hardware languages. 3. Architecture, memory, and timing. 4. The ASIC design flow. And finally, 5. Acing the interview. Let's just dive right in.
Chapter 1. Laying the Logic Foundation. You know, you really can't build a house without pouring the concrete first, right? Think of binary and hexadecimal math as your raw materials. Boolean algebra and De Morgan's theorems, those shape your materials into basic logic gates. From there, combinational logic groups those gates together into things like multiplexers and adders so your system can make instant decisions. And then, sequential logic introduces the absolutely crucial element of time, using latches and flip-flops to actually give your circuit a working memory.
Now, what's really fascinating here is the sheer weight you need to give to finite state machines, which are explicitly called out in the source material as being very important. Once you've wrapped your head around combinational and sequential logic, you combine them to create these FSMs. They are literally the brains of your digital logic, dictating the exact sequence of operations in any complex circuit.
And a massive structural pillar in that FSM foundation is nailing down the difference between Moore and Mealy machines. So, in a Moore FSM, the output depends purely on the current state. But in a Mealy FSM, it depends on the current state and the current inputs. Mastering these transitions and optimizing your sequence detectors on paper is exactly what prevents catastrophic logic bugs from ever making it into your final silicon.
Chapter 2. Mastering hardware languages.
Okay, listen up because this is huge. If there is one single concept you take away from this entire explainer, it's that mastering Verilog HDL is classified as the most important phase of your entire learning journey. I mean, this is the industry standard tool you'll use to literally describe your digital circuits to a computer.
Think of Verilog's syntax as your actual engineering tool belt. Defining modules and ports sets your hardware boundaries, while choosing between a wire and a reg data type dictates how the data physically moves around. You're going to use continuous assignments to build out those instant combinational paths, and procedural blocks, like your always blocks, to really breathe life into your sequential logic. Oh, and to make sure that code is scalable, you'll leverage parameters and generate blocks.
So this maps out exactly how your Verilog syntax translates directly into RTL, or Register Transfer Level Design, because once you actually know the language, you apply it to create real hardware structures. You'll be coding sequential and combinational elements like counters and FIFOs. You'll translate those Moore and Mealy state diagrams straight into FSM code, and eventually, you'll work your way all the way up to coding basic industry-standard communication protocols like UART, SPI, and I2C.
Moving on to Chapter 3, Architecture, Memory, and Timing.
So if your logic gates are the individual workers on the line, this infrastructure is the entire factory. Your chip doesn't just exist in a vacuum, so you really have to understand the hierarchy of the warehouse. Everything from flash memory down to blazing fast SRAM. And inside the CPU factory floor itself, you'll be orchestrating how the data path and control unit work in tandem with the register file to execute instruction cycles and pipelines at absolute lightning speed.
But hey, speed always brings problems, doesn't it? Imagine a world-class symphony playing completely out of sync. Well, that is your circuit without an understanding of timing. Which brings us to metastability, a totally unpredictable, unstable state in sequential logic. It happens when signals just don't arrive exactly when they're supposed to. In chip design, metastability is your absolute worst enemy. Seriously, a single timing error here has literally caused million-dollar chip failures in the industry.
Taming that kind of chaos requires precise timing control. We're talking evaluating synchronous versus asynchronous resets and performing really rigorous setup and hold time analysis so your data is perfectly stable before and after a clock edge. It also means you have to safely navigate clock domain crossings, ensuring that incredibly fast and incredibly slow signals can actually talk to each other without completely corrupting your data.
Chapter 4. The ASIC Design Flow.
All right, so we've got our logic, our code, and our timing constraints. What's next? Well, this simplified sequence is basically your map for turning that raw code into physical silicon. It kicks off with simulating your RTL code. Then comes synthesis, which translates your code into actual logic gates. From there, you jump into physical design, floor planning the layout, placing the components, building the clock tree synthesis, and routing all those tiny little wires. After a final static timing analysis, the flow outputs a GDS2 file. That is the final blueprint that gets sent off to manufacture the chip.
And finally, Chapter 5, Acing the Interview.
We have officially made it to the final inspection phase. Let's be real for a second. If your goal is to transition your career into digital design, we aren't just learning this stuff for fun. We're doing it to get hired. Every single fresher applying for these roles learns the basics of gates and flip-flops. So the fundamental question is, how on earth do you prove to an interviewer that you possess the advanced, practical insights that leading semiconductor companies are actually looking for?
First off, you've got to be prepared to flawlessly dodge those classic interview traps. A favorite insider test is asking you to explain exactly when to use blocking assignments with an equal sign versus non-blocking assignments with a less than equal sign in Verilog. Answering this one correctly proves you understand how to avoid simulation race conditions, and it shows you know how the simulator actually evaluates sequential versus combinational logic.
Interviewers are going to aggressively hunt for your blind spots in practical design safety. They'll want to see if you know how to avoid accidental latch inferences, which can totally ruin a chip, by the way, or if you genuinely understand what unknown or high impedance logic values will do to a live circuit. They're also going to expect baseline verification knowledge, so expect them to probe your grasp of test bench architecture and basic assertions just to prove your design behaves the way you say it does.
But if you want a real competitive edge, the source material highly recommends studying the stuff most freshers just skip right over. If you really want to stand out, get familiar with System Verilog for RTL design. Go learn low-power design concepts like clock gating and power domains. Get a handle on CDC-aware RTL design. Bringing these kinds of industry-level practices into an entry-level interview will literally instantly elevate your profile.
And finally, get ready for the whiteboard. Interviewers absolutely love tossing out practical, on-the-spot design problems. You might be asked to design a traffic light controller, a vending machine, or maybe an elevator controller. These are classic problems designed to test your ability to synthesize everything you've learned. You'll have to take those basic logic gates and FSMs we talked about way back in Chapter 1 and build them into a fully optimized system right there in front of them.
So this 13-phase blueprint condensed into these core steps gives you a massive competitive advantage. It completely cuts through the noise and tells you exactly what you need to focus on. But you know, a blueprint is just a piece of paper until you actually start building. So which of these critical components are you going to dive into first to land your dream engineering role? Take that first step and start laying your foundation today.